Okay, let's unpack this. If you are responsible for, say, a commercial kitchen, a specialized industrial process, or maybe even a fueling station, you know that fire suppression isn't just about having a red can on the wall.
Oh, not at all.
It's about complex, engineered, fixed systems. Today, we are stepping deep into the granular, often overlooked world of fire safety standards. Specifically, the 2021 edition of NFPA 17, which is the standard for dry chemical extinguishing systems.
It might sound dry, pun absolutely intended, but this document is so critical.
Right.
It really acts as the foundation for life safety and property protection in these environments where, ordinary water or sprinklers just won't work.
Or it could even make things a lot worse.
Exactly. NFPA 17 provides the minimum requirements for the entire life cycle of these systems. So that means everything from the initial hazard assessment and system design to the specific plate materials you have to use, installation, testing, and this is the big one, the long-term maintenance.
Our sources today are the actual chapters of NFPA 17 itself. It's dense stuff, highly technical. But our mission for you, the listener, is to kind of act as your expert guides. We're pulling out the core insights, the architecture, the, frankly, fascinating chemistry of the agents, and the extremely rigorous protocols, so you can walk away understanding what it takes to install and, more importantly, keep these systems ready to go.
And we should probably start by establishing the authority behind this document.
Yeah.
These standards aren't just dictated by one group.
Right.
NFPA standards are developed through a consensus process, which is then approved by ANSI, the American National Standards Institute. This process brings together engineers, manufacturers, users, regulators, insurers, just a huge variety of viewpoints.
So when you look at a rule in NFPA 17, you're looking at something that a lot of very smart people have argued about and agreed on.
A massive detailed consensus, yeah.
That sounds really reassuring, but there's a crucial disclaimer the NFPA makes that I think anyone in this field needs to know.
Oh, for sure.
The NFPA does not independently test or evaluate or verify the accuracy of anything in their standards. They're providing the best document based on current knowledge, but you have to rely on your own professional judgment.
And critically, seek the advice of a competent professional.
Right. It tells you what to do, but it doesn't absolve you of the responsibility of knowing how to do it right.
Precisely. And anyone working with this standard has to remember they're dealing with the current edition. That means any tentative interim amendments, TIAs, or any errata that are in effect. The rulebook is always being fine-tuned.
Okay, so right from the start, the scope is pretty narrow, isn't it?
It is. It covers systems that discharge dry chemical from fixed nozzles or hand hose lines using an exhalant gas. That's what we call a two-phase flow system.
And the standard really hammers home the qualifications of the people involved.
It has to. Section 1.6 is unambiguous. It explicitly states that only persons who are trained and designated by the authority having jurisdiction shall be considered competent.
So this isn't a DIY project for the maintenance crew.
Not even close. You need specialized expertise, and it's mandated.
That really sets the stage for the level of precision we're about to get into. This is highly pressurized, specialized chemical delivery.
And here's where it gets really interesting.
It's time to talk chemistry. When we say dry chemical, I think most people picture, I don't know, a dusty powder, maybe like baking soda, but this is highly engineered stuff. What exactly is this agent and how does it actually put out a fire?
So the definition in the standard, section 3.3.6, calls it a powder of very small particles.
Yep.
And they're typically based on sodium bicarbonate, potassium salts, or monoammonium phosphate.
Okay.
But the crucial part isn't just the chemical base. This powder is specially treated with other materials
Why is that?
to give it three vital properties.
Mm-hmm.
Resistance to packing, resistance to moisture absorption, which the standard calls caking, and to maintain proper flow capabilities, even after sitting in a tank for years.
So the system's usability really hinges on its physical state, not just what it's made of. If it cakes, it fails.
That is the ultimate failure mode, period. If the powder solidifies, the gas will just blow a hole through the mass and nothing will come out the nozzle.
And the standard has a very specific definition for that failure, doesn't it?
It's almost tactile. Caking means agglomerations that do not crumble into particles when you drop them from a height of 4 inches onto a hard surface.
A 4-inch drop test? That's incredibly specific.
But yeah.
It really underscores how critical the physical properties are.
It's a very practical on-site test for whether your agent is still viable.
Okay, so moving to the fire itself. What's the mechanism here? It's not cooling like water.
No, it's a totally different world. Dry chemical relies on something called chemical flame inhibition.
Oh, okay, break that down.
Essentially, the particles get heated up, they decompose, and they release substances that interfere with the free radicals in the flame.
Free radicals being the highly reactive bits that keep the fire going.
Exactly. It's like throwing tiny chemical wrenches into the engine of the fire.
That's a great analogy. It just stops the engine from running.
But, and this is a huge but, we have to stress a note from the annex, the effect of a dry chemical system is often transient.
Transient, meaning the effect goes away almost as soon as the agent cloud dissipates.
Right. If you still have a heat source and a fuel source, the fire can come right back.
So you have to remove the fuel source. It's a two-part solution.
It has to be. If you has a gas leak, you shut off the gas immediately. Otherwise, the fire reestablishes.
Okay, let's get into the three main chemical bases because their applications and their cleanup are very different.
Let's start with the classic. Sodium bicarbonate-based agents, regular dry chemical.
HCO3.
That's the one. It's primarily for Class B fires, flammable liquids and gases, and Class C electrical hazards. It's a great chain reaction breaker.
And it has a special trick up its sleeve, particularly for kitchens.
It absolutely shines with cooking oils and fats. Sodium bicarbonate agents react with hot grease through a process called saponification.
Saponification, so it literally turns it into soap?
It forms a soap-like layer. It's dense, non-combustible, and it floats on the surface, creating a barrier. It stops oxygen from getting to the fuel and stops vapors from getting out.
Yeah?
That prevents reignition.
That is an amazing mechanism, turning burning grease into fireproof soap.
It's why it's so common in restaurant systems. But for Class A fires, like wood or paper, it only stops the surface flaming. It won't get a deep smolder.
Okay, so what's next? What's the more powerful option for Class B risks?
That would be the potassium salt-based agents, things like potassium bicarbonate, potassium chloride. They're also BC rated.
And they're generally better at putting out flammable liquid fires.
They are. They're recognized as being more effective, faster chemical chain reaction breakers than the sodium salts.
But there's a big except here, isn't there?
A huge one. Despite being more powerful for general Class B fires, they're not generally recommended for deep fat fryers.
Why not?
Because they don't reliably create that saponification layer. So you get a faster knockdown, but you risk a very rapid reignition in a deep layer of grease.
So it's a trade-off. Faster on solvents, but less specialized for cooking oil.
Exactly. Which brings us to the all-rounder.
A multi-purpose agent.
Multi-purpose dry chemical. Monoammonium phosphate. NH4H2PO4. It's effective on B and C fires, like the others, but its real defining advantage is its effectiveness on Class A hazards.
Wood, paper, cloth.
Right, and it tackles those in a completely different way.
How does it do that if the others only handle surface flames?
When monoammonium phosphate hits a hot surface, it decomposes and melts into this sticky, glassy residue.
Okay.
This coating adheres to the surface and smothers the glowing embers. It acts as a glow retardant, excluding oxygen and stopping that deep-seated smoldering fire.
So it's a physical coating, not a chemical reaction in the flame itself.
Exactly.
3 different agents, 3 different philosophies: saponification, chain breaking, and this glow retardant coating, which I imagine is why you absolutely cannot mix them.
That is one of the strictest rules in the entire standard, section 4.7.3. Different types of dry chemical agents shall not be mixed.
What happens if you do?
The annex warns that mixing them can generate dangerous pressures inside the tank. It can literally cause the container to rupture. Or it can form chemical lumps that clog the whole system.
So you could have a catastrophic failure during a recharge if you're not careful.
It's a critical inventory control issue. You can't make that mistake.
And while we're talking about the aftermath, the residue, the cleanup.
This is the major downside to all of these agents. Dry chemical is not a clean agent.
What are the long-term hazards once the fire is out?
The residue, if it gets exposed to heat over 250 degrees Fahrenheit or humidity over 50%, can become highly corrosive.
And conductive.
And electrically conductive. The standard is clear.
Yeah.
Prompt cleanup isn't optional. It's essential.
And the type of chemical determines what it corrodes, right? Acidic versus basic.
That's right. The multipurpose agent, monoammonium phosphate, and potassium chloride are slightly acidic. With moisture, they'll eat away at steel, cast iron, aluminum.
And the bicarbonates?
Those are slightly basic. They can be corrosive to aluminum, brass, bronze, and titanium.
So even after the fire is out, the agent you chose dictates which materials in your facility are now at risk of long-term damage.
Correct. And remember that sticky, molten residue from the multipurpose agent.
Yeah.
Cleaning that up is a Nightmare. It requires scraping and washing. You are trading immediate fire suppression for a significant remediation headache.
So putting out the flame is the easy part. Managing the corrosive mess is the long, expensive part.
It really changes the risk calculus for the building owner.
Okay, one last piece of the chemistry puzzle. The delivery mechanism, the expellant gas.
Right. To shoot this powder across a room, you need a propellant.
And the rules for that gas are just as strict, especially about moisture.
Incredibly tight. If you use carbon dioxide, it has to be 99.5% pure. The water content can't be more than 0.01% by weight. That's a negative or 30-degree dew point. And the oil content has to be less than 10 parts per million.
That negative 30-degree dew point is so specific. Why the obsession with getting every last drop of water out?
Because water is the mortal enemy of a dry chemical system. Any moisture you introduce will start the caking process. It'll compromise the flow, and it can cause internal corrosion in the tank itself.
And for nitrogen.
The standard is even stricter. Industrial grade with a dew point of negative 60 degrees or lower.
So we've got the chemistry and the propulsion down. Let's talk about where this all gets used. So what does this all mean for protecting actual hazards?
Well, NFPA 17 lists 7 specific types of hazards that these systems are designed for. It's a pretty broad list. You've got your flammable liquids and gases,
Makes sense.
combustible solids that melt, like plastics, electrical hazards, think big oil-filled transformers,
Okay.
textile operations with flash fires, ordinary combustibles, but usually only with that multi-purpose agent, and of course the big one, restaurant hoods, ducts, and cooking appliances.
But the standard puts up some big warning signs for flammable liquids and gases, doesn't it?
It does. For flammable liquids, since the effect is transient, there's a serious risk of reflash if you don't remove all ignition sources.
And for flammable gases, it's even more dangerous.
It's an explosion risk. If you don't stop the flow of gas, the system puts out the flame, but now you're just filling the room with an explosive gas mixture.
Which could be ignited by what? A hot surface?
A hot surface, static electricity, anything.
Yeah.
Stop the flame, but you must stop the fuel.
Okay, so that establishes the boundaries. Now, what about the exclusion list? What can you absolutely not use dry chemical on?
This list is critical. First, chemicals that have their own oxygen supply, like cellulose nitrate. You can't smother something that doesn't need external oxygen to burn.
Right. Second, combustible metals.
Exactly. Metals like sodium, potassium, magnesium, they react violently with common agents. They require their own special Class D agents.
And the third one is a bit tricky, especially given the multi-purpose agent.
Deep-seated or burrowing fires. Think of a fire smoldering deep inside a bale of cotton or a huge pile of paper. The dry chemical just can't penetrate to the actual point of combustion.
So even the multi-purpose agent's coating can't get in there.
It can't. It's a surface agent. It's not like water that can soak in and cool the core.
And there are specific prohibitions just for the multi-purpose agent, right? Mostly because of that sticky residue.
Yes. It's explicitly prohibited for use on delicate electrical equipment.
And here's the kicker. The burden is on the owner, isn't it?
It is. The standard says before you even select dry chemical for any electronic equipment, you, the user, must evaluate the effect of the residual deposits.
So you have to decide if the corrosive cleanup is going to be worse than the fire damage you're trying to prevent.
That is a huge decision point for anyone managing a data center or a high-tech manufacturing facility.
Okay, let's shift to how these systems are actually built, the architecture.
We're looking at 4 core system types: total flooding, local application, hand hose lines, and pre-engineered systems.
Let's start with total flooding. The idea is to fill an entire room with the agent.
Correct. Discharging dry chemical into an enclosure. The key is that the enclosure has to be permanent and sound enough to hold that concentration of agent.
And this is where NFPA 17 gets incredibly specific with its leakage rules.
This is one of the most precise engineering bits in the whole standard. The total area of unclosable openings, gaps, vents, whatever, can't be more than 15% of the total surface area of the room.
If it's more than 15%, you just can't use total flooding?
Generally, no. And there are tiers for compensation.
Okay, so what's the baseline?
If your openings are 1% or less of the total area, you don't need to do anything. That's considered acceptable leakage.
But once you go over 1%, you have to start adding more chemical.
You do.
So say I have an enclosure with 3% leakage. How do I compensate?
If you're between 1% and 5%, you have to add supplemental dry chemical. The rule is 0.5 pounds per square foot of that extra opening area.
And you just add that to the main tank. It goes through the regular system nozzles.
Exactly. You're just increasing the total mass of the discharge to account for what's going to leak out.
But what if the leakage is worse, say 8%?
Now it gets more serious. If you're over 5% but still under that 15% cap, the compensation requirement doubles. You need 1 pound per square foot of unclosed opening.
And it's not just more chemical at that point, is it? The delivery method changes.
That's the key shift. The compensation must be provided by local application over the openings, at the same time as the main flood.
So you're not just beefing up the total charge, you're actively targeting the leaks with dedicated nozzles to create a chemical barrier.
Exactly. It's a much more complex piping and nozzle design. You're trying to build a curtain of agent to hold the main flood in.
And no matter what, speed is everything. What's the time limit?
For engineered systems, you have to achieve design concentration in all parts of the enclosure within 30 seconds. That's your window.
Okay, what about local application systems? This is for when you don't have an enclosure.
Right. If the hazard is out in the open or the room just doesn't meet those tight leakage rules, the idea here is to discharge the agent directly onto the fire. Think dip tanks, spray booths, outdoor transformers.
What's the biggest challenge you have to account for with local application?
Wind. The annex explicitly warns that you have to consider the effects of wind or any stray air currents.
Because a cross breeze could just blow the agent cloud right off the target.
And then the system is useless. So you might need physical barriers, or you have to adjust nozzle placement and flow rates to compensate.
Makes sense. Next up, hand hose line systems. Are these meant to be the primary protection?
Absolutely not. The standard is very clear. They are primarily supplementary.
So they're a backup to fixed nozzles or portable extinguishers.
Yes. They should not be used as a substitute unless the hazard absolutely cannot be protected any other way, which is a very high bar to clear.
And if you do use one, it has to be able to run for a certain amount of time.
A minimum of 30 seconds. And here's that two-phase flow problem again. The annex warns that if your flow rate is too low, the powder will separate from the gas inside the hose.
And you get an uneven, sputtering flow.
Or you just end up venting gas.
Yeah.
The velocity has to be high enough to keep the powder suspended.
Okay, finally, the most common type, pre-engineered systems.
These are the backbone of many installations. They have predetermined flow rates, nozzle pressures, pipe sizes. Everything is figured out ahead of time.
So the engineering burden is different. You're not doing complex calculations on site.
Right. All the hard math and fire testing has already been done by a listing agency like UL. The designer's job is much simpler, but also much more constrained.
How so?
You have to stick precisely to the manufacturer's installation manual. The exact pipe lengths, the exact fittings, the exact nozzles. Any deviation instantly voids the listing.
Got it. Let's shift now to a really specific area that's deeply regulated by this standard, commercial kitchens.
Commercial kitchen systems are a critical application, and they almost always use pre-engineered systems. They had to comply with the UL 300 standard, which is all about performance on hot grease fires.
And the main theme for kitchens seems to be unified protection. If one thing catches fire, everything gets covered.
That's the mandate of simultaneous operation. All the cooking appliances, the hoods, the branch ducts, everything in a single hazard area has to be protected by systems designed to go off at the same time.
A fire in one fryer triggers protection for the whole cooking line.
And the ventilation above it, yes.
How is the fire actually detected in that kind of hot, greasy environment?
Yeah, usually with thermal elements, so fusible links or heat detectors. You have to have at least one above each cooking appliance and at least one inside each exhaust duct opening.
Now, what about a huge kitchen, like in a hospital, where you might have multiple systems feeding into one big vertical duct? The common exhaust duct problem.
That requires serious coordination. The standard gives you two main ways to handle it.
What's the first method?
Method one is the simultaneous operation of all the independent systems that feed into that common duct.
So if you have 5 separate cooking areas and one has a fire, all 5 systems discharge.
Yes, because the duct itself is the shared hazard that can spread the fire between all 5 areas.
That sounds messy, but I guess it's necessary. What's the second option?
Method two is to install a dedicated, separate system that only protects the common duct riser itself. So when the system in Area 1 goes off, it triggers its own local protection and that dedicated duct system. It protects the riser without necessarily setting off the systems in all the other areas.
That makes a lot of sense. But no matter which method you use, the next requirement is maybe the single most important safety measure of all.
The shutoff requirement.
Yeah.
Absolutely critical. When the system actuates, All sources of fuel gas, whatever, and all electric power that produces heat to the protected equipment must be shut down automatically.
It's the only way to deal with the transient nature of the agent and prevent reflash.
Exactly. The system isn't just a fire extinguisher. It's a mandatory energy kill switch.
Is anything exempt from that?
Just one thing. Steam from an external source, and critically, the shutoff devices have to be manually resettable.
That's a simple but vital safety barrier. You can't just flip a breaker and start cooking again.
It forces a qualified technician to come in, assess the scene, and physically reset the safety controls before that hazard can be brought back online.
Okay, here's something that seems counterintuitive. Do the big exhaust fans have to shut down?
This is a really interesting exception. The standard says no. Exhaust fans and dampers do not need to be shut down.
Really? Wasn't that just suck the agent out of the hood?
You'd think so, but the annex clarifies that these systems are successfully fire tested under both zero flow and high velocity flow conditions. They're designed to work with the fans on.
Wow. Okay, let's quickly touch on a couple of other specialized hazards. Vehicle fueling stations.
Another high-risk area.
Hmm?
The protected zone is very specific. It has to include the full area within the arc that the fuel hose nozzle can reach.
So the entire potential spill zone.
Exactly. And just like kitchens, all the fuel dispensers have to shut down automatically when the system fires.
And what about massive mobile equipment, like mining trucks?
For those, you can only use listed pre-engineered systems, and they have to include a listed detection system. Manual-only actuation is only allowed if the AHJ, the authority having jurisdiction specifically, signs off on it.
Makes sense given the operator might be incapacitated.
And if there's a time delay on the discharge, you have to have both audible and visual alarms to warn personnel to get out.
Okay, we've covered the what and the where. Now we have to get into the how, the engineering that holds it all together, piping and controls.
This is where the physics of dry chemical systems get really complicated.
System integrity has to be paramount, especially when you're talking about this high-pressure, two-phase flow moving a solid powder suspended in a gas. What are the basic material rules for pipes and fittings?
They have to be non-combustible, and they're limited to galvanized steel, stainless steel, copper, or brass. Black steel is okay, but only if it's in a non-corrosive atmosphere.
And what's strictly forbidden?
Cast iron, aluminum, and any non-metallic pipe. Cast iron is too brittle. Aluminum can be corroded by some of the agents, and plastic just can't handle the pressure or the flow.
The pressure calculations for this stuff seem intense. It's not just based on the normal operating pressure.
No, it's much stricter. The pipe wall thickness has to be calculated based on the greater of two things. Either the normal charging pressure at 70 degrees Fahrenheit, or, and this is the tough one, 80% of the maximum pressure the tank would reach at its maximum storage temperature.
So you're designing the pipe to handle the pressure on the absolute hottest day possible with a safety factor built in.
Exactly. It's non-negotiable structural safety. Yeah. Now let's talk about actually installing it, which gets so complicated because of that two-phase flow.
Right. Solid particles in a gas just don't behave like water.
Not at all. The annex warns designers that the flow of dry chemical does not follow general hydraulic theories. Every time you have a change in direction, like at an elbow or a T, the heavier powder and the lighter gas want to separate. The powder wants to go straight, the gas takes the easy way out.
And that's a huge failure point. If you have a T that's supposed to split the flow 50-50 to two nozzles, but all the powder goes to one side,
then one side of your hazard gets no protection. The system fails.
So how does the standard make you compensate for that?
For engineered systems, the designer has to use special tricks. Sometimes it's a Venturi device right after the T to remix everything. Other times it's a specific arrangement of elbows to create turbulence and keep the powder suspended and distributed evenly.
That is some seriously sophisticated engineering just to fight gravity and momentum inside a pipe.
It's why you need that competent professional. And this extends to the pipe supports. You can't just use ordinary hangers.
No conduit clamps or C-clamps. Why not?
Because the supports have to prevent lateral movement during discharge. When that high-pressure slug of gas and powder hits an elbow, there's a massive amount of thrust, like a rocket engine.
But at the same time, they have to allow the pipe to move in another direction.
They have to permit longitudinal movement for thermal expansion and contraction. So they have to be incredibly strong in one direction, but flexible in another.
Okay, and pipe prep before assembly is just as precise.
The pipe has to be reamed and cleaned. And after it's all put together, you have to blow the whole network out with dry gas, like nitrogen, before you install the nozzles.
To get rid of any debris that could clog them up.
Exactly. Any little bit of metal shaving or cutting oil could compromise that tiny nozzle orifice.
All right, let's talk about making the system go off, the controls.
Actuation redundancy is the key phrase here. Fixed systems have to have both automatic detection and a manual way to operate them.
And they have to be independent of each other.
Completely independent. The failure of one cannot affect the other.
And the placement of that manual pull station is really specific.
It is. It has to be in the path of egress, and the center line has to be installed between 42 and 48 inches above the floor.
A very tight window. That's clearly based on accessibility studies for emergencies.
For sure. Then you have system supervision. If the system needs electricity to work, for the detection or the release, it has to be monitored by a supervisory alarm and have a backup power supply.
So a simple power outage can't take out your fire protection.
Right, but there are a couple of key exceptions.
Do.
You don't need monitoring if the system has a fully mechanical backup for detection and actuation.
Okay.
And in kitchens, if the system is interlocked with the cooking equipment so that a power failure automatically shuts off all the fuel and heat sources.
Then you don't need to monitor the suppression system's power because the hazard itself has been shut down.
Exactly. It's a brilliant piece of interlocking logic. The power failure becomes the failsafe.
Okay, let's circle back to personnel safety. A dry chemical discharge is a pretty dramatic and hazardous event for anyone in the room.
Oh, yeah. The standard has a big caution warning about it. The discharge causes severely reduced visibility and temporary breathing difficulty. It's a blinding, choking cloud of powder.
So what safeguards are mandatory if people could be exposed?
The goal is prompt evacuation and rescue. So you need a whole list of things. Personnel training, warning signs, pre-discharge alarms to give people a chance to get out, and discharge alarms.
And for the aftermath?
You need to provide respiratory protection for responders and have emergency eye wash stations nearby. The planning has to account for the agent cloud itself as a hazard.
So the system is designed, the pipes are installed, the safety protocols are in place. The last piece is proving it works and keeping it ready.
Which starts with the documentation imperative in Chapter 10. You need formal plans drawn up by a trained person for all engineered systems.
And those plans have to be incredibly detailed.
They do. Dimensions of the hazard, types of combustibles, air handling info, and of course the exact chemical quantity, flow rate, and nozzle locations.
And these plans have to be approved by the AHJ before you start work.
Absolutely. Because as we've said, one small change in pipe geometry can kill the whole design.
Once it's installed, you have to prove it works with acceptance tests.
Right. And here's where it gets interesting. How do you test the piping for blockages without using water?
You use dry gas.
Correct. You have to do a flow test using nitrogen or dry air at normal operating pressure to verify that every path is clear.
And you absolutely do not hydrostatically test the pipes.
Never. Introducing water into those pipes would be catastrophic for the future of the system.
So you prove the plumbing works without introducing the one contaminant you've spent all this time avoiding.
Exactly. Then the installer has to certify that everything complies with the plans and the listing.
Okay, let's talk long-term readiness, Chapter 11. Who is ultimately on the hook for this system for decades?
The owner. Always. You can hire a contractor, but the responsibility rests with the owner of the facility.
And what does the owner have to do every single month?
The owner does a monthly check. It's purely visual. You're just verifying it's in the right spot, the manual actuators aren't blocked, the tamper seals are intact, and the service tag is current. If you find anything wrong, you have to call a technician immediately.
That's the basic check. But the real detailed work comes from the certified tech, and it happens on a strict schedule.
That's the service technician maintenance. And it's required at least semi-annually, every 6 months.
And this has to be done by a trained, certified technician.
Absolutely. And it's an exhaustive check. They're looking at everything. Detectors, containers, piping, nozzles.
And they have to physically check the chemical itself for caking.
That's the most important part. They have to examine the dry chemical, and if there's any evidence of caking, it has to be discarded and the system recharged.
We talked about those thermal detectors in kitchens, the fusible links. Do those have to be replaced every 6 months even if there's no fire?
They do. Fusible metal alloy links must be replaced at least semi-annually. The annex explains that in a greasy environment like a kitchen hood, contamination can actually change the temperature at which the link will melt.
Wow, what about the restorable heat detectors?
Those can stay in service, but they still have to be inspected, cleaned, and tested every 6 months.
Beyond the semi-annual check, there's a much more invasive inspection required for the tanks.
Yes, the 6-year internal examination. For stored pressure containers, the ones that hold both the gas and the agent, you have to completely empty them and do a full internal and external examination every 6 years.
That's a huge undertaking. Depressurizing, disassembling. Why every 6 years?
2 reasons. First, to make sure there's no internal corrosion in the tank. Second, it's the ultimate check on the condition of the dry chemical itself.
And when this is done, the tech has to prove it.
They do. They attach a weatherproof label, and most importantly, they install a verification of service collar around the neck of the cylinder.
What's the point of the collar?
The collar is definitive proof that the valve was actually removed from the cylinder. It shows they didn't just weigh it or do a surface check. It proves they did the full internal exam.
Okay, finally, the ultimate pressure check. Hydrostatic testing.
Hydrostatic testing is required every 12 years. That's for the containers and the hose assemblies. They get pressure tested to make sure they're still structurally sound.
Are there any common exceptions to that 12-year test?
Yes, a few. Very large containers over 150 pounds, some very small auxiliary cylinders, and any cylinders that have a DOT3E marking are exempt.
We've covered a ton of ground here, from the corrosive risks of monoammonium phosphate to the specialized two-phase engineering for the pipes and these mandatory clockwork maintenance schedules. It's so clear that these aren't just fire extinguishers. They are complex, high-pressure, chemical delivery systems that demand incredible rigor.
It really is a lesson in highly specific readiness. Every single detail, from the -60-degree dew point on the nitrogen to that 4-inch drop test for caking, is there to make sure a powder can do its job instantly.
And we noted earlier that this extinguishment is often transient. The effect disappears quickly. We also covered how multipurpose agents are limited from use on sensitive electronics because that residue is so corrosive and hard to clean up.
Right. If that powder hits a server rack or a control panel, the cleanup required to prevent long-term damage is going to be intense and very expensive.
This raises a critical question for any facility manager relying on these systems in a high-value or high-tech space. The standard imposes these stringent, fixed-schedule maintenance protocols. Monthly checks, semi-annual service, 6-year internal exams, 12-year hydro tests.
All of which represent a known, significant ongoing cost.
Precisely.
Yeah.
So, given that you've chosen a residue-producing agent, given the high long-term maintenance costs, and given that the fire suppression itself is transient, the ultimate question for you to mull over is this. How does the cost and complexity of maintaining the system's readiness compare to the potential non-fire property damage caused by the discharge residue itself? It forces you to consider what the true long-term risk mitigation strategy really is when you're using an agent that is transient in effect but potentially permanent in its consequences.
That's a fascinating and sometimes very uncomfortable decision point when you're designing protection for a modern facility.
That's all the time we have for this deep dive into NFPA 17. Thank you for joining us.